Hey there, and welcome to The Explainer. Today, we are putting on our detective hats. We're going to tackle a classic puzzle, a real brain teaser that's one part mystery and one part mathematics. You and me, we're about to crack the case of the red ball.
So, here's the fundamental question, right? An event happens. You don't see it, but you see the result, a single clue left behind. The big question is, can you work backward from that clue to figure out how likely the hidden cause was? That's exactly what we're going to learn how to do.
All right, every good mystery needs a setup. You got to have a scene of the crime, right? Well, this is ours. And it all starts with something pretty simple. 2 bags.
Okay, let's get the lay of the land. Here's our evidence board. We've got bag A with 3 red balls and 4 black balls inside. Then you've got bag B, which has 4 red and 5 black. Got it? Everything's clear, everything's accounted for? Well, for now.
And here is where the plot thickens. Something happens in secret. 2 balls, we don't know which color, are taken from bag A and moved over to bag B. This one little move, done in the shadows, completely scrambles the situation and kicks off our entire puzzle.
So, before we can even think about solving this thing, we have to do what any good detective would do. We have to line up all the potential suspects. What could have possibly happened during that secret transfer? We need to list out every single possibility. And when you break it down, there are really only 3 ways this could have gone. Let's call them our main scenarios. First, scenario E1. Both of the mystery balls were red. Second, scenario E2. It was a mix, 1 red and 1 black. Or third, scenario E3. Both of the balls were black. That's it. One of these 3 things has to be what happened.
Now, here's a super important point. These 3 scenarios, they are not all equally likely, not even close. So before we find any new clues, let's just figure out what the odds were for each of these things happening right from the get-go.
We can actually nail these probabilities down with a little math. Don't worry, it's just a fancy way of counting. It turns out there are 21 different ways you could possibly pick 2 balls from bag A. Out of those 21 ways, only 3 of them give you 2 red balls. A whopping 12 of them give you 1 of each color, and 6 of them result in 2 black balls. Just look at this. It makes it so clear, right? That middle scenario, E2, where 1 red and 1 black ball were moved, was by far the most likely thing to happen from the start. I mean, it had more than a 50-50 shot. This is our starting point, our gut feeling before we get any new evidence.
But things are about to change. A clue has just been found. This is that moment in the mystery where the detective finds the footprint by the window. We have a new piece of information, and now we have to go back to our suspects and see how well their stories hold up.
And here it is. This is the big one. After that secret transfer, somebody reaches into bag B, pulls out 1 ball, and it is red. This is our clue. This single red ball is the key that's going to help us unlock what really happened in the past.
Okay, let's play this out. We're going to interrogate each scenario. First up, suspect E1. Let's assume for a second that this is what happened. 2 red balls got moved. If that's true, bag B would now have 6 red and 5 black balls.
So in that world, the E1 world, the chance of finding our clue, of pulling out a red ball, is 6 out of 11. That's actually a pretty high probability. Scenario E1 gives a pretty good explanation for the evidence we found.
All right, now for our next suspect, E2. What if this one happened? What if 1 of each color was transferred? Well, in that case, bag B would now be holding 5 red balls and 6 black balls. See, in this world, the chance of finding our red ball clue drops a little. It's now 5 out of 11. So scenario E2, which was our favorite suspect at the beginning, doesn't explain the new evidence quite as well as the first one did. Interesting.
And now for our final possibility, our long shot, E3. What if it was 2 black balls that got moved? That would leave bag B with only 4 red balls, but a total of 7 black ones.
And in this world, the odds of drawing a red ball are only 4 out of 11. So scenario E3 does the absolute worst job of explaining our clue. It makes the evidence we actually found seem pretty unlikely.
Okay, we've got all the pieces on the board. We have the initial odds for each suspect. We know how well each of their stories explains the clue. It's time. It's time to put it all together, weigh all the evidence, and deliver the final verdict.
And the tool we use for this, our secret weapon, is called Bayes' theorem.
Seriously, just think of it as a logical machine for detectives. You feed in your initial suspicions, you feed in the new evidence, and it spits out exactly how you should update your beliefs. It's amazing.
So what are we asking this machine to do? We're asking this, what's the new probability of our first scenario, E1, given the fact that we found a red ball? Bayes' theorem has a formula that just combines everything we already figured out, those initial odds and how well the clue fits, to give us a new, updated belief. It lets us see which suspect is now the most likely culprit.
And the verdict is in. After running the numbers, the new updated probability that 2 red balls were transferred is 3 out of 10. The probability for 1 of each color is now 5 out of 10, and for 2 black balls, it's 2 out of 10. So get this. Even though our first scenario was a long shot to begin with, finding that red ball made it a much stronger suspect. But in the end, our initial frontrunner, E2, is still the most likely cause. Case closed.
So yeah, we solved the puzzle, which is cool. But the real lesson here isn't just about a number. It's about this incredibly powerful way of thinking. This method of starting with a result and logically, carefully working your way backward to find the most probable cause.
And that's why this is such a game changer. It gives you a rock-solid framework for reasoning backward. It makes you stop and consider every possibility, not just the one that feels right. And crucially, it teaches you exactly how to balance what you already believed with the new facts, which helps you avoid that classic trap of just assuming all explanations are on an equal footing.
Which leaves us with one last question for you. I mean, this isn't really about balls and bags, is it? Think about a doctor trying to diagnose a symptom, or a mechanic trying to figure out why a car won't start. When was the last time in your life that you had to work backward from a piece of evidence to figure out the most likely cause? It happens all the time. Thanks for joining us.